The laser is a relatively new invention, but its development really started at the beginning of the 20th century. As early as 1917, Albert Einstein developed a theory for stimulated emission of radiation. However, the first laser was not built until 1960. The real breakthrough as regards the industrial application of lasers came in the beginning of the 1980s. The number of laser applications has grown enormously over the past decade, and this trend is expected to continue into the 90s. Nowadays, lasers are used for cutting, welding, and marking. They also find uses in communication, in measurement technology, in medicine. The range of applications stretches from the automotive sector to integrated circuit production. In this film, we will concentrate mainly on cutting, using a CO2 laser. Materials processing with a CO2 laser consumes gas. A laser gas is necessary to generate the laser radiation. For cutting and welding, a process or assist gas is also required. The carbon dioxide laser, or CO2 laser, is the laser type which is most often used for cutting of metals and other materials. The laser light is generated via an electrical discharge in a gas-filled glass tube. Two mirrors, one of which is partially transmitting, make up the ends of the tube. The laser is filled with a gas mixture in which carbon dioxide is the laser-active gas. The other gases are helium and nitrogen. However, the laser gas mixture contains only about 5% carbon dioxide. The major constituent in the laser gas is helium, which, thanks to its good thermal conductivity, facilitates heat removal. This is vital because 80 to 90% of the electrical energy which is pumped into the laser is dissipated as heat. Nitrogen is also an important component of the laser gas. About 15% is normally present. Nitrogen's role is to assist the carbon dioxide molecules in attaining the desired vibrational state. A laser radiation is generated as a result of transitions between different vibrational states of the carbon dioxide molecules. A laser light is amplified by reflection between the mirrors in the laser cavity, and finally leaves the cavity via the partially transparent mirror as a laser beam. This beam is transmitted over some distance, which may be short or quite long depending on the type of system. Finally, it reaches the processing head where it's focused to a small spot by means of lenses or mirrors. Laser gases must be of high purity, often 99.995% or better. The quality requirements are thus stringent, not only on the gas in the cylinders, but also on the gas distribution system. Regulators should be the installation should be made by properly trained people who know exactly how to handle and fit the components. Undesirable impurities which enter the laser cavity may well result in loss of power, uneven performance, and reduced service life for vital optical components. By the end of 1989, almost 10,000 CO2 lasers will be processing materials around the world. Most of these will be used for laser cutting. What particular advantages does the laser offer for cutting? First of all, most materials can be processed. Complicated shapes with very small radii can be cut with excellent precision and quality and with a minimum of waste. And since the heat from the laser beam is highly concentrated, there is little or no distortion of the cut parts. In general, the maximum thickness which can be cut by laser is about 10 millimeters for metals and roughly 50 millimeters for other non-metallic materials. Gas cutting and plasma cutting normally find application for thicknesses above 10 millimeters, so there's little competition between these methods and laser cutting in processing steel, for example. Laser cutting is primarily an alternative to mechanical methods such as punching, blanking, or nibbling. Although laser welding has hitherto not enjoyed the same rapid growth as laser cutting, a considerable increase in the number of CO2 lasers for welding is predicted in the near future. Laser combined with small heat-affected zones and little distortion. The welds are narrow and have good penetration and excellent appearance. A single run is normally sufficient. Welding can be performed at high speed to give a metallurgically clean weld metal with good properties. Consumables are normally not required. The main drawback with laser welding is that it requires very careful joint preparation and fixturing. Laser welding is normally achieved via the so-called keyhole mechanism. The pressure from vaporized metal creates a tunnel through the melt. Molten material is forced backwards from the front to the back side of the keyhole and forms the weld. An important and fast-growing application for laser welding is in the production of automotive transmission and motor components. Laser welding is also being considered by many automotive companies as an alternative to spot welding for body assembly.